All right. Okay, so the last topic for alternating currents is rectification. We'll start with this topic and we'll finish it in this class. In the from the previous topics that we have done, of course, excluding transformers because that's not included. Is there any question whatsoever?
No, sir.
Okay, so did you guys go through the worksheet by yourself?
Yes.
Right. So any questions from the worksheet?
No.
All right. Okay. So let me. Okay, so let's start rectification, right? For now, forget the name rectification. We know that an alternating current, if I plot it, the alternating voltage supply looks like this. Sorry, this here we have time. Here you can have either V or I, let's say I. And so it's a varying current that goes in both the directions. These are two values, which is the amplitude of this alternating current, the maximum or the peak current, and the minimum current. Now, generally, you know, if you have, for example, your r.m.s coming from the main supply is, let's say it's 220 volts, right? What would be the peak voltage for 220 volts? How do you compute that? You take your r.m.s.
1.1.
Okay, all right, yeah. So you exactly. So and you multiply it by square root of 2. So when you do that, you get 311.1. Okay, so this is the voltage, which means that these peak values are 311.1. Let's ignore that 0.1 for now, right? So let's ignore that. 311 plus with 311 and then minus 311 over here. If you were to measure this gap between these two numbers, it's a big gap, right? From 0 to 311, and then on this other side you have minus 311. This gap between these two values or voltages is huge, right? And this huge gap, let's suppose that if you were even able to use a transformer and step down your voltages or the current, right? So this is, let's just call it, this is the voltage axis. So if you were to able to step down your voltages, let's suppose you brought it down to 12, right? Even then you have plus 12 and you have minus 12 volts. There is a significant gap between these two voltages. And if you look at this graph, you see that it is constantly varying. And usually in some countries, the frequency of that is 50 hertz, which means it moves like this. In 1 second, it would move 50 times, oscillate like this. It will alternate between the two currents, right? Between the two directions. Now, if I were to use this type of supply in some electrical appliances, usually your electrical appliances, for example, let's suppose you're using a computer, right? A computer is not capable of handling these significant changes in the voltages. If you give a computer a varying voltage that changes from plus 311, from 0 to 311, and then goes to minus 311, in very less amount of time, because it's doing that 50 times, right? It's doing that 50 times. So that means that uh, it's constantly changing its voltages, and the computer is not capable of handling that, right? The components inside a computer will just blow up because they cannot handle uh, these significant changes in the voltages. So what we can do is, we want to make or to change this supply to a constant, at least almost constant current or constant voltage. Let's call it some V r.m.s. Sorry, this would be V naught. Okay, right? So in this case, the current or the voltage is constant at every point in time. So there is no changing voltages, which means that there would be no changing voltages inside the components of the computer, for example, and of course, then it will not blow up. We want to go from this thing to this thing. And the question is, how do we do that? Okay, so before we go to that, is there any question from this thing? Do you understand the problem that we have at our hand? Is the problem understood?
Yes, sir.
Okay. So what we can do is, we can use what's called a diode. Now, what's a diode? It is a device or a component that allows only a particular direction of current to flow. Right? So the symbol for a diode usually looks like this. It's a triangle with a line over it. So this is what a diode, the graphical symbol for diode looks like. And the job of it is to only allow current to pass one way, right? So in this case, the arrow, or you can think of it as an arrow, which is pointing to the right. So the only current that can flow is in this direction. There will be no current that can flow in this direction, because that's the job of the diode. Now, the current, if I connect this diode to supply it, let's do that. So this is, suppose that this is your circuit, and let's say that this is your diode, right? And you can just say that your electrical appliance can be modeled as just a resistor R, and let's connect this to this circuit. Over here, you have some alternating voltage supply, and let's say this is some V input that I'm giving it to. There will be a potential drop happening because the current that flows through the resistor, it's going to obviously cause a potential drop across this R. Let's call that V out. This only happens when the current flows in this direction. So that means that the current flows through the diode, and the diode conducts and sends the current to the resistor R. When the current flows through this resistor R, it causes a potential drop across it according to V equals IR. And if the input voltage is in the opposite direction, suppose instead of going here, it was going in this way. Then because there is a diode in the circuit connected, this current is not even going to make it. It's not going to flow in this direction at all. And if it does not flow in this direction, there is no current in this direction, Yani, and that means that there would be uh, no potential drop across this resistor R, right? And now what does that look like? So suppose again, what we have done here graphically, let's see what happened, right? Let's again plot this graph. Remember, originally you have something like this. What happens when I connect a diode across it? Again, you have to remember, diode only allows current to flow in one particular direction only. So what will happen is, for this circuit, if I draw this axis, this is again T, this is V. So what happens is that the current flows in one direction, and there is some potential drop happening across the resistor R, right? When the current flows in one direction. So again, you know, alternating current, first it goes in one direction and then it changes its direction. And then it repeats that cycle on and on. So first, what will happen? The current will flow in one direction. So we'll get something like this. But now the current is not allowed to flow in the opposite direction, right? And if there is no current flowing in the opposite direction, for that amount of time, there will be no potential drop happening across this resistor R, right? And so you would get no potential drop. So it would be 0 for some time, like this. And then what happens is, again, the current changes its direction. And when the current changes its direction, it starts flowing again in the opposite way, which is this one. Because now when the current changes its direction, it's flowing through this, the current is flowing through the resistor, causing a potential drop V out. And so we see that potential drop like this. And then this keeps on happening. Now, again, the current changes its direction in the opposite way, and diode does not allow that current to flow. So the potential drop again is 0. And then again, when it changes its direction, there is some potential drop. This type of a thing is called half wave rectification. Any questions from this thing so far?
Sir, how did this halfway form?
You mean you're talking about this
Yes,
graph,
the
right?
parts where it went 0.
Okay, so what happens is, initially you just turn on the voltage supply. You have connected a diode. This diode is only allowing the current that is in this direction to flow in the circuit. So again, we have an alternating current. So the current flows, for example, first it starts to flow in this direction. It encounters a diode, but the diode says, yes, you can pass through. So it comes to this resistor R and it flows through this resistor R. According to Ohm's law, there will be some potential drop across this resistance R, which is given by V is equal to I times R. And you would observe some potential drop happening. And then that is done. There is no other component on after this resistor R. So it just, now the current changes its direction because it's an alternating current, right? So first it flows in one direction, in the next cycle it flows in the opposite direction. So now when it flows in the opposite direction, because the diode is only allowing this directional current to flow, this part of the current is not going to flow in the circuit at all. There will be no current for that amount of time where it had changed its direction. And so that's why we observe a zero voltage. So there is this gap between these two curves. And then again, what happens? It does not allow the current to flow. Then after that cycle, it changes its direction again. The current changes its direction again. Now it goes back in this direction. And the diode allows it to flow. And so it again causes a potential drop across the resistor. And then in the same way, now it changes its direction again. So the potential drop is zero because that current is not allowed to flow, and so on. Right? So is it clear? Omar, is it clear?
Yes, sir.
Okay. So that's half-wave rectification. Any other questions? Okay. So if I look at the voltage still at this graph, I still have a problem, right? Okay, we don't have an entire opposite directional voltage happening, but there is still a significant drop in voltage. And apart from that, we also have this thing that in some time interval, there is absolutely no potential through that resistor, or there's no potential drop happening. So there is no current flowing, which is not ideal for if you use this in any electrical appliance. For some time, it's just going to stop, and then again it will start, and then it will stop, and then it will start, which is also not ideal, right? You don't want that. So we need to fix that problem.
Sir, sorry,
We
I
can
have a
fix that
question.
problem.
I
Sorry?
have a question. Would this affect the power?
Yes. Would this affect the total
Yeah.
power? Okay, so what is power? Power is V times I, right? So the total power that is supplied is a constant. Your voltage and current vary accordingly for that, right? So the power, your electrical appliance might be rated at some power, and it will provide you that power by changing the voltages and current, right?
Yes.
So now we can let's go to the next page. We can fix this problem by what is called a bridge rectifier, right? Don't let the names intimidate you. If you find the names intimidating, just ignore them. A bridge rectifier is a combination of diodes connected together, right? It looks like a diamond shape. Let's see if I can draw that. Yeah, something like that. And there are diodes connected in this way. Over here, it's like this. Then here you have another one, but it's in this direction. And then over here you have final, which is again in this direction. So you can see the both the sides, they are parallel to each other in this. This is a bridge rectifier, right? So this is what it's called, a bridge rectifier. It's a combination of diodes connected together. What will this do? Let's see. If I take this and put it in my circuit, let me just copy this thing so that I don't have to draw it again. Let's suppose that here I have my circuit, and suppose I connect this device over here, and then the current flows through whatever resistor or anything that it has to flow through, right? So what will happen is that okay, so suppose that here you have an alternating current supply, some AC source. Again, we can call it any potential Vn, right? And on the right hand side, you will have any resistor, right? A resistor as in any electrical appliance connected. Okay, so what happens now in this case? If the current flows in this direction, what will happen? It will go take this path. Actually, let me use another color for this. So if it flows in this direction, it takes this path, it goes here. It cannot go on this side because the diode does not allow that directional current to flow. So it's going to go in this direction. When it goes in this direction, when it comes over here, it cannot go back in this direction because again, the diode does not allow that. So what it does is it flows through the resistor R. So that's one of the directions of the current that flows through the resistor R. Let's look at the second one. If I choose this direction, what happens is it goes over here. It cannot go to the left because the diode does not allow it. It goes in this rightwards direction in this way. And when it goes over here, after that, it again goes through the resistor R because it cannot go back in this way as the diode is not again allowing. So in this case, we are having voltage drops both the times, right? We are having voltage drops both the times, as in the current is flowing in one direction, you have a voltage drop. The current changes its direction with this blue one that you can see. Still, there is some current flowing through resistor R. So the voltage drops are happening in both the cases, which means that this will look like this graph. So let's suppose here you have T, you have V, and it will look something like this. So one direction, there's some voltage drop. The current changes its direction. Again, there is some voltage drop. Again, current changes its direction. There is some voltage drop. And so this pattern keeps on repeating on and on. Right? So this thing is called a full wave rectification. Is that clear?
Yes, sir.
Is it clear? Oh, okay. Any no questions from this? Okay.
Sir?
But now look at this thing. There is still some problem in this thing because we're going to zero voltage for very small instant, and then again we are going to peak, and then again we are going to zero, and then peak, and then zero. So there is still this change, a significant change in voltage happening. There we can get rid of this change as well by using a capacitor. right? Let me see how much time, 5 minutes. Okay, so let's see, we can finish this and that. Now we know capacitors very well. We know that they store energy, which means that they will store some potential across the plates of the capacitor. So what I can do is I can connect this bridge rectifier. So let me see if I can again draw it quickly. This one. I take this and I connect it to a capacitor like this. And then after that, you connect any resistor, as in your electrical appliance over here. Let's say this is R. This is some capacitor of capacitance C. Okay, now you know that this will store charge, energy, which means it will store some potential difference across the plates. There will be some potential difference, and it will store that. The bigger the capacitor I have, the more voltage I can store. So in this case of alternating currents, we want the highest amount of capacitance that we can choose for our purposes, right? So we want a very big capacitor. Okay, so what happens in this case now? You'll again see there is no AC supply. Let's just connect it over here. So suppose this is some AC supply. If the current flows in one particular direction, for example, suppose that the current flows like this, it's going to go in this way. Connecting an AC supply over here is not a good idea. We should connect it over here. This one. So if the current goes in this way, again, I'll use some other colors. It's going to go through this direction, this direction. It will not go, actually, it will go through this other direction as well. And then it will go through this one, and this one. So it's still the same. This is still the same that was happening before as well. But the difference is in this capacitor that we have connected, right? And that difference is that when it flows through this capacitor, it stores some potential instead of completely going to zero. Now the capacitor has stored some potential for the use later. So what happens to your graph, if I, let me just take this one, the full wave rectification, and let's modify this graph. So this is what we have without a capacitor. Now I connect the capacitor because the capacitor stores some charge. It's going to look something like this. Instead of completely dropping to zero, it's going to come to this point. And then again, it will increase and then drop a bit down. And then again, it will go like this. Sorry, like this. So now what we have done is, by storing some of the potential, we have minimized the potential. I'll not use the word potential drop, but the change in potential, we have minimized that as much as we can. Now, this red color wave that you see is a much more suitable form of supplying the voltages to any electrical appliances. This, compared to full wave rectification and half wave rectification, this one is much more closer to our goal, that was to convert it to the direct current. This graph is much more stable than both half wave and full wave rectification. This thing is called smoothing, right? Because what we have done in this case is we have smoothed the output by output produced by using a capacitor, right? So any questions from this?
No, sir.